Oh, hey. I guess we're on. Wow. Okay. Let me start with actually an announcement. Can you go down to the pad? It has to do with quizzes. Yes. And the announcement is actually that from now on, they're actually going to be at 8:45. Yeah, here. Afterwards, you're welcome to leave. So that's when they are. All right. We'll think about it. Maybe they'll be Monday morning or something at 9. Okay. Okay. That's a possibility. Then people will be leaving all during the class, getting up at every 30-second intervals and getting up. Okay. Since I dashed in today, I guess I can't say anything. Okay. Last time we looked at this idea of impedance and admittance. So the idea is this, is if you have some electrical element and the relationship between the voltage and current is given by multiplication in the frequency domain, so multiplication of Laplace transforms, then you say it has an impedance description. So here, this says that the voltage, the Laplace transform of the voltage is the Laplace transform of the current times the Laplace transform of something, which we'll name later. This is called the impedance of the device. And what happens is if you work out the equations that a circuit satisfies, they are absolutely identical to the equations you saw in 101. They are absolutely identical, except in 101, voltages, currents, node potentials are all real numbers, like 3, 5, 12.2. Now, they're all Laplace transforms. Everything is a Laplace transform. So this is not unlike, in fact, it's just one step beyond sinusoidal steady state and phasors. There, you extended static analysis to sinusoidal steady state analysis by assuming every current and voltage was a sinusoid. You then represented its amplitude and phase by a complex number. And then you observed that even complicated things like inductors and capacitors could be expressed by a relation that looked very much like a resistor relation, or Ohm's law, except that everything is complex. Okay, so this is really the exact same story, except it's a little bit more complicated now. It's everything inside is a Laplace transform. Okay, so last time also, that's the basic idea. Last time we looked at writing down this. This is simply the solution of a circuit. That's it. That's just an explicit description of the solution of a circuit. And it explains it in terms of a bunch of things. This is, U of S is a vector that contains the Laplace transforms of all the driving voltages and currents. W is a big vector that contains all of the information about the initial conditions of the circuit, like initial inductor currents and initial capacitor charges. These have different names. This part is called the natural response of the circuit, and this part is called the forced response, or the zero, some people call it the ZIC response, because that's the zero initial condition response. So some people call that ZIC response here. Now, an interesting fact is that the forced response is linear in the Laplace transform of the input signal. That, of course, means that all voltages and currents in a circuit, in a linear circuit, are given by convolution of the input signal with something, with, in fact, the inverse Laplace transform of this. And we're going to talk about that in detail. So if we go back to that example, simple example from before, here, to find the natural response, you set the source to 0, so that becomes just a short, and it's a series RL circuit. You know exactly what the solution is. The solution is simply that the current decays exponentially, like I of 0 e to the minus t over capital T. You multiply by R to get the voltage, and that's this. Okay? So that's the natural response. And the forced response says, assume 0 initial current. Once you do that, it says that this inductor is basically an impedance. The impedance is SL. Okay? Now, this circuit is exactly the same. You can now do anything you could do with resistive circuits, except now you're manipulating Laplace transforms. So, for example, here, a very simple way to do it is by the voltage divider rule that says that the voltage here is this voltage times this voltage divided by the total, sorry, this impedance divided by the total impedance. This impedance is R, that's R plus SL. So, again, this is as if it were the second week of 101. You write down that the Y forced response is U times R over R plus SL. The big difference here, of course, is that everything inside is a Laplace transform of something. Taking the inverse Laplace transform of this, we find that that's given by a convolution. It's this. So altogether, the output voltage is given by the natural response plus this forced response. And if you go back and check, you'll find out that's exactly what the solution is. That's what it is. So that is the, that's just a simple example before we had worked out the general case. Okay. Now, because static circuit analysis from 101 and now complete dynamic analysis from 102 satisfy exactly the same equations, it says that pretty much everything you know from 101 works here. For example, you can do things like, let's see, series and parallel combinations, voltage-current divider rules, things like Thevenin-Norton equivalence. Everything works. Nodal analysis, everything works. The difference, of course, is everything is now a Laplace transform of something. So that's the only difference. And it has lots of interesting implications. It says, for example, if you actually wrote a circuit analyzer in 101, right, that manipulated real numbers and solved linear equations, if you could actually overload the operations to manipulate Laplace transforms, which are complex valued functions of a complex variable, then your very same code would actually now solve general dynamic circuits. That's pretty amazing. That's sort of the idea here. So let's look at an example. We won't do too many of these. We'll just sort of do a handful of examples. Here's a complicated circuit. It's got resistors, capacitor, inductor. It's not that complicated, but for hand analysis, it's complicated. And let's find the input impedance. So the input impedance is simply the ratio of this voltage to this current. Laplace transforms, of course. And also, what I'm beginning to do is what actually people do usually is, once you get used to this, people actually now know, we refer to capital VN and capital IN as the voltage and current. Okay, so I mean, once you get sophisticated here, you just kind of go back and forth between the Laplace transform and the time domain signal without even mentioning it, not even a verbal hint. So for example, some people would just say, what's the impedance? It's the ratio of the voltage to the current. To be perfectly technical, it's the ratio of the Laplace transform of the voltage to the Laplace transform of the current. So, okay. So here, how do you do this? Well, first of all, this thing is just described by a set, a not small set, of algebraic and differential equations relating voltages, branch currents, node, all sorts of things. But this might as well be 101. We just replace this with 4S, and the impedance of this element here is the product of the impedances divided by the sum. It's 4S divided by 1 plus 4S. That's here. Then this is a series combination of three things. It's 1 over 2S. That's the impedance of a capacitance, 2 farad capacitance, and the impedance of a 3 ohm resistor is 3. So I get this. This is the impedance of this whole thing here. And I could, if I wanted, I could simplify that. It doesn't make any difference. But the point here is that the Laplace transform of the voltage is the Laplace transform of the current times this, which is the impedance. Now, it's kind of interesting. If you look through here, you can even understand what some of these things mean. For example, let's actually see if we can even understand this here. When you see the 3, if I take the inverse Laplace transform, what does the 3 turn into? It's a delta, right? And so that's something which appears in a convolution equation. So this says that part of the VI relationship, there's a component which relates the instantaneous voltage to the instantaneous current, and the ratio is 3. Okay? Why is that? Well, look, there's a 3 ohm resistor. So when you pump a current through here of some current, you will instantaneously get a voltage here, which is 3 times that current. That adds to it. Then you see, what's this 1 over 2s? What does that mean? In the time domain, what does that turn into? What's the inverse Laplace transform of this? Just a half. And so in the context of convolution, it says that part of the output voltage is 1/2 convolved with the input current. That's the integral of the input current. What here has anything to do with what relates the integral of the input current to a voltage? Exactly. Okay? So, and so forth. I mean, this is how it works. Okay? So, and it's important also, I guess from the simple point of view, you have all the nice calculations here that you can do these little calculations by hand as if it's 101. What I'm trying to stress here is don't lose sight of don't do mindless calculations, right? It's important to understand what each of these terms mean, to understand exactly what the 3 means physically, and the same with the 1 over the 2s. Okay. Yeah.
What if you don't have like 0 initial condition? How would you go about solving the problem?
That's a good question. So what if you don't have 0 initial conditions here? Can you make this statement in that case? No, it's false. If there's not 0 initial conditions, there will be something else out here. In fact, it will be V natural of S. There'll be this extra term here, which is the natural response, and that's due entirely to the initial condition of the capacitor and the inductor here. That's this one. Okay? So what you can do is you can analyze these separately. Okay? So that's what you can do. Okay. And in fact, this is probably the trickiest thing here is to get straight the difference between when you have an impedance and when not. Right? What is absolutely wrong is the following, is that when you have a non-zero initial condition, to even imagine that there is an impedance description. There never is. There's no such thing. Right? It's an additive term. We'll do another example here. This is just to demonstrate nodal analysis. So here's again a simple circuit. And the node equations are exactly as they are in 101. So here, for example, we're going to solve for the 2 node potentials E1 and E2. This is ground, I guess. And we form a matrix, G, on which the diagonal elements are the sum of the total conductance tied to that node. So for example, the conductance that tied to node 1 is 1/3, that's this guy, plus 1 ohm, 1 mho for this one, right? And then the impedance of a 2 farad capacitor is 1 over 2s. Its conductance is 2s. Okay? So that's 2s. So I should have 1/3 plus 1 plus 2s, and hopefully that's what I have here. That's what I've got, and so on. And you work it out. I mean, for example, the off-diagonal element in the conductance matrix is precisely minus the sum of the total conductance tied between the nodes. So here's E1 and E2. That's 1/3 plus 2s, and maybe that's what it is. Yeah, it is, right. Okay? So here we end up with a 2x2 set of equations. It is identical to what you'd see in 101, except that all the data structures would all be real numbers. Now they're Laplace transforms. Okay? So 2x2 is, of course, sort of the limit on the size of linear equations. I personally recommend a person solving by hand. And so we could work this out. I mean, you work out what the determinant is and all that in a simple formula. And it might get ugly, but the point is you'd work out the exact solution of what E1 of S is and what E2 of S is in terms of In of S. Okay. Final example is things like Thevenin and Norton equivalence. So again, everything is the same, and the reason it's all the same is because the fundamental equations are all the same. So Thevenin equivalent of this circuit, it's actually quite interesting. It's a Thevenin equivalent with a time-varying voltage, right, and an impedance. So Thevenin equivalent, I think in 101 is a pretty natural thing. It's not hard to explain to somebody. What you do is you say, well, what I do is I draw various amounts of current out of this battery, for example, and I measure the voltage, and the voltage looks like this or something like that. And that's the VI curve, and you say, okay, that's the Thevenin equivalent. It's a resistor in series with a voltage source. Okay? This seems pretty simple. This is substantially more sophisticated. Here, it's a circuit described by a set of differential equations. It's a time-varying voltage source. and yet this thing has a Thevenin equivalent. So for example, here you can find the Thevenin voltage by just looking at the open circuit voltage, which is a voltage divider rule, and so on. Now it's kind of sophisticated here. A voltage divider rule, in this case, you have to remember, is actually solving a differential equation, right? When you write, Z1 over Z1 plus Z2 and divide, right, division in Laplace transforms is sort of like multiplying by the inverse. You're actually solving a differential equation when you divide. After a while, you don't care, doesn't mean anything to you, and you just say it's 1 over 1 plus 2s. You don't even think about it. But you are, in fact, solving a differential equation. Okay, so everything works the same. I won't go into the details because it's basically just 101 material. But you end up with something that looks like this. It's a new voltage. It's not the same as the old voltage. We could take the inverse Laplace transform if we like. It's got a constant, it's got an e to the minus t term, and it's got an e to the minus t over 2 term. Okay? Then it goes through a single impedance, which is 2s over 1 plus 2s. Okay? And that's just sort of the way that works. Is there a question?
Would that be enough to express in terms of the v Thevenin and the z Thevenin? Do we need to transfer back to the time domain?
No, that's another interesting thing. If you wanted, you can now transform this back to the time domain. But what will happen more and more is that you won't. Right? You just won't. You'll just leave it this way. So this is very common. And in fact, in a lot of fields, people actually just the language spoken is in the frequency domain. Right? To the extent where many people then have actually forgotten what convolution is, for example, but have very detailed knowledge, intuition, and understanding of frequency domain stuff. It's very strange, but that's the way it works. Right? Yeah, so we could, if you like, we could go ahead and transform to the time domain and then express this that way. Then we'd express the Thevenin equivalent. It basically says that there's a convolution equation that relates the voltage and current. That's basically what it says.
Can I ask you how you got the calculation for V Thevenin? It looks like you kind of did a voltage divider.
Yeah, well, of course, there's a reasonable chance it's just wrong. So, but I'm happy to check it. I think I did do a voltage divider. Here's what I should have done, and we'll see if it's in fact what I did. I take the Laplace transform of this, and I should get 1 over s minus 1 over s plus 1. And if you multiply that out, you get s plus 1, and you get s plus 1 minus s is 1, and actually that's what I got. So this is okay. That's the voltage source. Then what I do is I do a voltage divider. It's that times 1 divided by 1 plus 2s. And I guess that's this. So this is okay.
Oh, I guess I was wondering, is the impedance of the inductor, is it 1 over 2s or is it just 2s?
It's 2s, right? And in fact, if you ever forget something like that, there's a lot. Soon you won't forget it because it'll be clear what that means and so on. For one thing, actually, you can go back to sinusoidal steady state analysis and just plug in s equals j omega to see what happens. Should be the same thing. But otherwise, what you do is suppose you forget it, or let's say, for example, you're having a midterm and you panic and you think, oh my God, is it 1 over s or 2? I don't know, and I'll just can't remember. So it's very simple. You just go back to this, right? V equals L di dt, and you take Laplace transforms, and you get V equals SL I, or L times SI. And there's your impedance right there. Okay, so that's, right? If all else fails, pop back to 101 and basically, or physics, and say what an inductor does.
Yeah, is S just simply the relation of j omega? Because S
No, it's
is...
not.
It's not?
No, it's a frequency variable.
Mm-hmm.
If you plug in s equals j omega, you get the impedance that you saw in 101.
Yeah,
But
it's just simply the like relation almost the frequency when you're at that zero initial state.
Yes, but this is different. S is just a dummy variable in a Laplace transform here, right? That's really just that's all it is. It is true if you plug in s equals j omega, you will recover sinusoidal steady state analysis that you saw in 101. But for here, it is just it's a dummy variable. It's traditional. Actually, at the turn of the century, this is about 100 years old, the turn of the century, the original term for S was P. I can't remember why, but there was some name for it. And then there was a different British system and an American system, and they fought. And I can't remember who won, who was S. Well, this was like, Newton and Leibniz fighting about notation for calculus, right? It's the same story. Yeah. Okay. Final topic for circuit analysis has to do with natural frequencies and stability. So if you look at the natural response, the most obvious thing to look at there is whether or not the natural response decays with time. If you have a circuit where the natural response decays with time, then what it really means is that the circuit forgets its initial conditions. That's what it really means as time increases. And that is the case when the poles of the natural response, which are the zeros of this polynomial, this determinant here, or this rational function, when these are zero. So these are called the natural frequencies of the circuit. Okay? And in in most cases, circuits are designed to be stable. In other words, left alone, the effects of the initial conditions decay. And in fact, it's quite common, that's so common that in fact often people don't even worry so much about the effects of initial conditions. And then people say, well, why don't you worry about it? And you say, well, I'm assuming they're zero. And someone says, well, is it true that they're zero? And you say, no. But whatever they were, for this circuit, their effect vanished within 12 microseconds. So after 12 microseconds, for all practical purposes, the initial conditions might as well have been zero. So this is sort of the idea. We won't go into great detail about this, but that's sort of the idea. Okay. This brings us up to a major topic which we've already seen a lot of things. We've already seen a lot of this, but this will just make it formal. And it's the idea of a transfer function and convolution. So first we'll start with convolution. You've already seen it, but now we're really going to go into horrible detail. At least now you know why. You know this describes, for example, any linear circuit to start with. It describes any mechanical system. It describes any sort of linear constant coefficient ordinary differential equation. Lots of things are described by convolution, so that's why we're going to study it. So here's a convolution system with input u and output y. And some people just write y equals h star u, like this. Okay? Do not write this, please. That's technically wrong, right? Because how does this parse if someone writes this? How do you actually parse that if you put your really mean, careful parser on? What happens? What's u of t? U is a signal. That means it's a function that takes a real, and then the parser sees u of t and says, oh, no problem, I know what that is. What is it? It's a real number, okay? Then it sees another real number, and it sees a star symbol, and it either decides that you don't know what you're doing, or it says that the person's trying to convolve two numbers, and it might do something like a nice parser error message here would be to check and say, did you really mean you wanted to convolve two numbers, right? Or are you just using a silly old symbol for multiplication? Okay, or something like that. Okay, so.
But Professor, don't we write y of t equals something all the time? Like,
Yeah, I'm talking about if you're being very, very careful. Yeah. Here, there's no reason to. This is the right way to do it. We do this. Look, I'll show you something that we do a lot. Y equals h convolved with e to the minus t. We will actually start writing that. Yeah, we will write that. That's informal. If there's people who are very technical or literal-minded in the audience or something like that, then you really shouldn't even do this. You're right, it's h star u or something, and then you say where u of t is e to the minus t. Okay? Okay, so it's given by this formula here. You've already seen this a couple of times. It didn't mean anything to you then. It will soon. So here, it's the integral of h of tau u of t minus tau d tau. It's the same, you can change variables here, and it's the same as h of t minus tau times u of tau d tau. Now the important part is you have two functions. It's an integral of a product, and you multiply together the two terms at times which add up to t. That's the whole point, is that tau and t minus tau is t, and the same here. Okay? Now in the frequency domain, this relation here is a lot easier to understand. It's simply y of s equals h of s times u of s. It says in the frequency domain, one signal is a multiple of another with this rate, this proportionality constant or whatever. That's called the transfer function of the system. So here, its inverse Laplace transform, this thing h, is called different things depending on the field, but the most common ones are the impulse response or the convolution kernel of the system. It has other names as well, but these are, I mean, every field then has its own name for these things, but probably the most widely used are impulse response and convolution kernel. And so people will write this in block diagram this way. Often people will just write it as a little convolution operator like this, but then as you start thinking in the frequency domain, it'll actually be written like this. What's amazing about this now is a convolution operator, right, now looks like a scaling system. That's the simplest system there could possibly be. It says simply that a signal coming in gets multiplied by a number like 2 or 12 or minus 5, and that gives you the output. So this is sort of like a scaling system, except that the scaling in front depends on frequency. And so then you'd call it a transfer function. Is there a question?
Would you want to write big U and big Y?
Yes, you would want to. And in fact, if you were being correct, this looks fishy, very fishy. You're absolutely right. If you're going to do this right, you'd make this U and big Y. And now it's actually correct that Y is H times U. This is just the sloppy notation that has evolved. And it relies on a lot of conventions. One convention is that you know that a capital H probably means a transfer function. But you're absolutely right. It's horrible notation, but hey, that's the way the language has evolved, and this is the way it's spoken on the streets. Okay? So, yeah. I mean, even worse, I don't think people would write this, right? That's I think over the line for me. But no doubt there are people who do, right? Right. I mean, this is really sick because it's kind of it's mixing time domain signals and then transfer functions and things like that. So, but no doubt there are people who do this, and it's in kind of little backward fields or I don't know, who knows. I'm sure there's people who write this and don't even think about it. Okay. So some important properties of convolution systems. First of all, they're linear. In other words, if you double the input to a convolution operator or a transfer function, what comes out doubles. And you have superposition as well. And then composition, this is very interesting. If you have composition, this corresponds to multiplication of transfer functions. Okay? So here, for example, if you see a system which first processes A by the convolution operator, by the transfer function A, and then by capital B to get Y, that's the same as if you simply you simply operated with a single transfer function which had transfer function BA, the product. Okay? Now, already this is not obvious, right? For example, if I write down a string of 4 transfer functions in a row, and say this describes a certain communication system. The first one is the transfer function of the amplifier that drives this thing. The second one is the RF amplifier. The next one is the transmission through a microwave link. The next one is this, and so on. Then writing down the transfer function of what happens end to end is simple. It's the product of all the transfer functions. There's almost nothing to think about, right? If then someone says, no, tell me what happens in the time domain, you now have to write down 4 convolutions and stick them together. You could do that, and you'd get this horrible 4-dimensional integral. Okay? So this is worth something, this way of thinking about it. Okay. Now what this means is kind of interesting. It says you can actually manipulate block diagrams with transfer functions as if they were scalars. And again, it's because the same equations are satisfied, right? The difference is when you multiply 2 things or something like that, you're not multiplying 2 real numbers. You're actually finding a new convolution system whose convolution kernel is given by the convolution of the 2 kernels there. Once you think about that for a while, you'll know why it is that people then start simply thinking in the frequency domain. Is there a question?
Outside of the
Mm-hmm. Oh, I'm going to tell you. Yeah, we're going to go into that in great detail. Okay. Yeah, right now I would say there's no reason any of you should have even the slightest intuition about it. We're going to fix that though. So, okay. Okay, so let's do an example. Here's a feedback connection. So G is some transfer function. In other words, it's a convolution operator. Well, here, this is basically, it's a big convolution equation. It says that Y is the convolution of little g with u minus y. So it's, in fact, it's a convolution equation. It's got kind of y, it's worse even than a differential equation. It's kind of got, or it's got y appearing both on the left and the right, and there's a convolution involved. It's not fun. Turns out, though, it's very easy to understand in the frequency domain. If we take the Laplace transform, we just get this, we get y equals capital G times u minus y. You simply, you put gy over here on the other side and you solve for it, and you get capital Y is g over 1 plus g u. Okay? And so you have the transfer function of the system from here to here, we say is g over 1 plus g. That's how you do it. Now after a while, you get very blasé about this. Doesn't mean anything. You just say, well, the transfer function is this, and someone says, are you sure? And you go and you do a side calculation, and you're basically just doing arithmetic or elementary algebra. The fact is, you are solving a very complicated thing. You are solving this integral equation. That's what you're solving, right? So it's, after a while, you forget that you're actually doing something complicated. I guess as with all good notation and good conceptual systems, after a while, you forget the fact, like linear algebra, you forget the fact that you are in fact doing something when you write down A inverse, where A is a 50 by 50 matrix. You forget, you casually write down A inverse. So what? Doesn't mean it, A inverse, no big deal. Well, you forget the fact that in fact, working out the inverse of a 50 by 50 matrix is actually a big deal, and nothing probably that no human being could ever do in a lifetime correctly, right? But you don't care. You just write down A inverse and so on. And so you just say g over 1 plus g. Who cares? Well, you just solved an integral equation. Okay. Let's look at some general examples. Here are some. Linear constant coefficient ODEs all give transfer functions. So here's the simplest example. Y prime plus y equals u. You take the Laplace transform and solve, and you get this. Now this, of course, assumes zero initial conditions. Otherwise, it's not given by a transfer function at all. Okay? So this says that here, when you see this differential equation, this now means a lot to you. I'll tell you what it means to you. What it says is, if y has zero initial condition, it says that y and u are related by convolution. They're related by convolution by e to the minus t. Okay, so this means that, and you can get that immediately. Here's an integrator. Well, the transfer function is 1 over s. Its impulse response is just 1. In other words, you're convolving a signal with the kernel 1. So in fact, from now on, 1 over s is going to mean an integrator system to you. And the truth is that people do not go around making block diagrams that look like this. Some people do. They do not do that, even though it's pretty. What you will universally see is the following. That's an integrator. Period. Okay? So the universal symbol for an integrator is simple 1 over s. Now you know why. An integrator is in fact a convolution system. It has a transfer function, and the transfer function is exactly 1 over s. Okay? 1 over s, its inverse Laplace transform is 1. That's the thing when you convolve something with 1, you're integrating it. Okay? So from now on, when you see a box that says 1 over s, it just simply means integration, and you don't even think twice about it. When you see s, what does that mean? Yeah, and when you see s cubed, what does that mean? It means triple derivative. It says that this thing is the third derivative of that. Okay? And in fact, this is just what people write. It's just, people are just too used to seeing s and Laplace transforms and transfer functions, so people don't even write, d cubed over dt cubed. They just write s cubed, and it means triple differentiation period. just that. So that's the way it works. Okay. Now for a delay, if you have a delay system, here it says that basically y of t is equal to what the input was capital T seconds ago. The impulse, this is also a convolution. It's convolution with a signal that looks like this. It's got an impulse at t equals capital T. And the transfer function is the Laplace transform of that is e to the minus st, like this. Okay? Now this is one where arguably the time domain description is simpler than the frequency domain description. Okay? Nevertheless, because people think in the frequency domain more often than not, the almost universal symbol in a block diagram for a delay is e to the minus st. So in fact, if you look at a block diagram and anything communications, anything at all, acoustics, anything like that, you will see e to the minus st, and from now on that simply means to you that is a delay of capital T seconds. That's what it is. Okay, so that's sort of the idea. And it's given by a transfer function. It's a convolution system. I mean, this is a case where, of course, the time domain description is pretty simple. The relation between one signal and another signal delayed capital T seconds is pretty easy, right? And you can understand it. Everyone has a good idea of what it is. But since everything else is done in the frequency domain, this means delay. Okay, and so these are things you'll see from now on. Okay, so you'll see these in multiple other courses and things like that. Okay, now circuits, same thing. We just saw from the last lecture precisely this, right? That if you have a circuit with linear elements, LCs, with no initial conditions, and then if you have any circuit voltage or current, then it's given by a transfer function where the circuit is driven by a single source. So, and these have special names. For example, if it's the voltage and current in a single branch, you call it the impedance. If it's the opposite, if you're expressing the current in terms of the voltage, it's called an admittance. When they're both voltages, it's called the voltage transfer function, or just the transfer function from one place to another in the circuit. And the same thing with currents. It's called the current gain, is another name for it, or the current transfer function of a system. Okay? So let's do an example. And actually, this is the first, here's quite a real one. So this is actually a very typical circuit, except for the values, which are all silly. But except for the fact that the values are all silly, this is in fact a type of amplifier you would, or a type of circuit you would in fact widely see. Okay, there it is, got little resistors, capacitors, things like that. Well, this is described by a complicated differential equation. Well, let's work out what happens here. Well, it's just like 101. What you do is you say, well, there's no current flowing in here. That's an ideal op amp. So the voltage here is a voltage divider rule. It's 1 over 1 plus 1 over S times V in. That's this. Okay? Then this voltage must equal that voltage, right? Because that's the point about an ideal op amp. Therefore, you know the voltage here and you know the voltage there. So therefore, we can figure out the current flowing through this resistor. It's this voltage minus that voltage divided by 1. And you sort of, you work that out, and you get that that's Vn over 1 over S plus 1. Okay? Well, this current, where does it go? It's coming through here. It cannot go down here because no current flows into there. So it's got to go through the parallel combination of a capacitor and resistor. Well, the impedance of that is 1 parallel 1 over S. And so you multiply that impedance times this current, and you get the voltage from here to here. And then finally, how do you get the voltage here? Well, it's this voltage minus that voltage, and so on. And if you keep going, you go through these term by term. I won't do it because I mean, you've done it many times in 101. And anyway, it's all the same. Except now you're manipulating Laplace transforms. But finally, the transfer function turns out to be something like this. 1 minus S plus 1 minus S plus 1 squared. And so sure enough, this means that the relation between this voltage and this voltage is given by a transfer function. Okay? Or in the time domain, it says that this is a convolution of this voltage with some function. What function? This one, delta of t minus e to the minus t minus t e to the minus t. So whatever that means, that expresses this voltage in terms of that one. It's a convolution. That's what it is. So what this is it's an electronic realization of a convolution operator. Right. Okay, let's look at one more example. This is a vehicle suspension system. So here's a simple second-order vehicle suspension system. Here the input is sort of the ground height or the wheel height. So the idea in this system is you take this ground height and you move it up and down like this. And of course, as a result, this mass also will jiggle up and down a bit. For example, if I move you up and down very, very slowly, what will y do? If I move you up and down very slowly and very smoothly, what will y do in response to you? It will follow you. Okay? On the other hand, if I wiggle you extremely quickly, what will y do? It'll wiggle lots or less. A lot less. Okay, that's the whole. In fact, that's the whole idea of a suspension system, right? So you have pretty good intuition about what this mechanical system does, right? You've got a pretty good intuition for it. If U is slow and smooth, Y tracks it. But if U is rapid, the motion in Y is far smaller, right? So if we work out the details, this is given by a second-order constant coefficient differential equation. You take Laplace transforms and solve, and sure enough, what you have is this thing is described by a transfer function. In fact, you refer to that as the transfer function from road height to vehicle height. Okay? That means they're related by a convolution. It says that whatever this your intuition was here about what happens, that's a convolution operator. That's what it is. So whatever it is that relates U to Y, it's a convolution. Yeah.
Like in that system, how would you find like the resonant frequency with the Laplace transform?
Well, let's see. I don't think we've actually, to tell you the truth, I don't think we've actually defined resonant frequency. But remember, this thing can have all sorts of different qualitative dynamics. There could be two real poles here, in which case you would not even, it wouldn't even make sense to refer to a resonant frequency. But otherwise, the resonant frequency, we'd find it out. It would be it might be the resonance, wherever the b squared minus 4km here number, the square root of that divided by 2a or something, 2m or whatever. That would be your, that would be the frequency at which it would sort of oscillate. By the way, that alone suggests all sorts of things about this, right? I mean, you also have pretty good, if this were underdamped, you should also have the following intuition about this, all of which we'll confirm analytically very soon. But if this thing is underdamped, and I take U, and I sort of wiggle it up and down very, very slowly, everything's fine. If I take U and wiggle it up and down extremely quickly, much faster than the resonant frequency, again, we're okay. But if I take U and wiggle it up and down, right at the frequency at which this thing likes to oscillate, I think you can figure, your intuition at least will strongly suggest what happens, right? What will happen? You will get a very, very large response is what will happen. Now in a mechanical system, that's probably a bad thing. In a suspension system, that's for sure a bad thing. In an electronic circuit where you're trying to amplify a sinusoidal signal, that's a very good thing. And that's actually why there they refer to the quality factor. And the less damp something is, the better it is. So if you do RF or wireless stuff, everything, your measure of merit is how resonant you can make something. Okay? If you do automatic control for vehicles like aircraft or automobiles, right, then having even slight underdamping is not good. This is not good. And if you have moderate underdamping, then you're actually in big trouble. Okay, so this is just another example of a convolution system. And let's see, we'll look at one more example, and that's a DC motor. Also something I think you've seen on some homeworks and things like that. So here it is. It's a little motor. A current goes through it, and basically the current you put through is going to affect the shaft angle, right? Because you put a current through it, and what happens is the thing spins up, and it starts spinning, and eventually it spins up to a certain speed where the losses are due to the mechanical friction exactly equal the power you're putting in, and so that's what happens, right? So here you'd have a mechanical resistance of the shaft and load, and that might be the total torque on the shaft is the electrical, the electromechanical torque minus the, this is the back torque due to friction. You add that all up, and this is Newton's law. This is just F equals ma, but for rotational systems, it's ma equals F, except here it's torque, angular acceleration, and rotational inertia. You take Laplace transforms of various things, and in fact, I have this vague memory that you did. Actually, that's what I think. Maybe this was maybe on a quiz or something we made up. I think, but I can't remember. So you end up with, in the end, with theta of s is k over js squared plus bs times I. Okay, and so this has a transfer function. Actually, I think on the quiz you did something even more sophisticated. You actually went from the voltage to the angle, and there was another layer of electrical differential equations, but I can't remember. Okay, so that's also a transfer function, and so people would say, you would talk about the transfer function from the current to the shaft angle. So this would be, for example, in a hard disk drive, or in a floppy disk drive, or something like this, or a CD-ROM drive. This would be people know lots about that transfer function. It's very important. It says that the relation between the shaft angle and the current is given by a convolution. In fact, you can even work out what it is. If we work out what this is, you can see what the poles are. There's one pole at s equals 0. Everybody see that? And then what comes out is js plus b here, like that. You rewrite it that way. And because of the 1 over s, the impulse response has what kind of a term in there? 1. It's 1. Okay? And in fact, then this one, k over js plus b, that's a convolution with a decaying exponential. So what it says is, just by looking at this, you can say, well, what relates the shaft, or if someone says to me, describe the shaft angle of a motor, how is it related to the input current? I would say, well, it's really two things. First of all, there's this term, which is convolution with an exponential. They'd say, why is that? And you'd say, well, there's kind of some damping, this mechanical damping, and when I put the current on it, the speed of the motor doesn't instantly speed up. It takes some time. Okay? Then there's the 1 over s term, and they'd say, what's that? And I'd say, oh, that's the integral. That's the one that relates the angular velocity of the shaft to the position. Okay? So I mention these things because what the power of all of these things like transfer functions and so on is that you can mindlessly manipulate things and just using algebra. That's very powerful because the things you're mindlessly manipulating are very, very complicated, right? It's also the danger. So it's good every now and then just to stop and look at what you have and make sure it makes sense. For example, if you made a little error and this looked like that, what alarms might light up? What would that mean if there was a minus sign there? It's unstable. It says it's given by a convolution system, except the convolution system has a growing exponential. Now, then you'd think and you'd say, wait a minute, the last time I checked, when you plug an amp of current when you plug 1 amp of current through a motor, the relation is not given by a growing, you don't get a growing, it's not given by convolution with a growing exponential. And this lights up an alarm that says that you weren't thinking, you were just manipulating symbols and making sign errors. Making sign errors is fine, but not thinking isn't. So that's sort of the idea. Okay, let me do one more thing, which is I'm going to take 1 minute to talk about interpretation of convolution, and we'll get back to that on Wednesday and talk about it in great detail. So here it is. If you're in a math class, there's nothing more to say, because what do you mean, what's convolution? That's convolution. There's nothing more to say. Okay, so on the other hand, there's a lot more we can say about this in terms of just interpreting it. What does it mean? How do you think of it? And here's the way I think of it, and then we'll continue this next time. So I think of this as a system. U drives the system. It's the input to the system, and Y is the output of the system. It's what comes out. Okay? So it says that what comes out of the system is an integral or mixture of what went into the system. That's what it is. Okay? Well, let's see. I interpret this variable tau as meaning seconds ago. That's what it means. Because u of t minus tau, that's what the input was. If now is time t, then t minus tau is what the input was tau seconds ago. And this says that the output now is an integral or mixture of what the input has been at various times in the past. Well, is it a uniform mixture? Then h of t would be 1. And in fact, that's what an integral is, of course. An integral is mixing what the input signal has been in the past uniformly. In other words, there's no extra weight on the recent past or the remote past. The weight is all the same. It's 1. That's an integral. When I put h of tau here, it's kind of like it's a weighted integral of what the input has been at various times in the past. If h of tau is decreasing, that says it's kind of like an integral, except that I'm going to put less emphasis on what the input signal was in the past. If h of tau is growing with time, that's the opposite of fading memory. It basically says that the recent past is far less important than the remote past for the system. Okay? So another way to say it is that h of tau, that's the impulse response, that tells you how much the current output depends on what the input was tau seconds ago. So that's the physical interpretation of what this means. And this is just some stupid examples, and then we quit. If someone walks up to you and has an impulse response and plots it, and you look at it, and you see something like this, someone plots it or measures it. This is fairly common. And you see that it looks like this. It's got a big bump like that around t equals 21, like that. What this says is that what that system does is it's a weighted integral of what the input was. It's got a little bit to do with what it was recently, and a little bit to do with what it was, say, 22 seconds ago and more remotely in the past. But mostly, the output depends very strongly on what the input was 21 seconds ago. Or if this was even tighter like that, you'd see you're getting something close to the impulse response of a delay. In other words, a perfect impulse. And that says it depends only on what it was 21 seconds ago, not what it was around 21 seconds ago. Okay, so I think we'll quit here, and then we'll continue this stuff next time.
Content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today, before we get into the meat of today's lecture, Matt has very kindly, Professor Evans, has very kindly agreed to do an experiment. Yeah. So for those of y'all who are in recitations, both he and Barton talked about polarization in recitation last week, and Matt will pick it up from there.
So back to the ancient past. This was a week ago. We had our hyper-intelligent monkeys that were sorting things that all seemed very theoretical. And in recitation, I said things about polarizers and said, look, if we use polarizers, we can do exactly the same thing as these monkeys. We just need to, set up a little polarization experiment, and the results are identical. You can use one to figure out the other. But I didn't have this or nice polarizers or anything to give a demo, so here we go. What I'm going to show you is that if we start with something polarized here with all white, and that's right now I have all vertical polarization here. And if I just put on this other box there, which is going to be another polarizer, if I put it the same way, this is all of our white electrons coming through all white. See, it doesn't really do much. And if I look at the black output over here, the second color sorting box, that's the same as turning my polarizer 90 degrees. So nothing comes out black. So this is if we remove this guy from the middle, you have just exactly what you'd expect. You sort here, you have white, and you get all white out. Great. Everyone thought that was easy. We all had that figured out. This box got thrown in the center here, and it became sort of confusing because you thought, well, they were white, so I'm going to throw my box in the middle here. That's this guy at 45 degrees. And then if I throw this guy on the end again, the idea was, well, they were all white here, so maybe this guy identified the soft ones from the white ones, and now we have white and soft, and they should still all be white, right? So I put this guy on up here. They should all come out, but sort of don't. And if you say, well, are they black? Well, no, they're not really black either. There's some sort of strange combination of the two. All right, so that's this experiment done in polarizers, but let me just play the polarizer trick a little bit because it's fun. So this is if I say vertical polarization, and then how many of them come out horizontal. So here I'm saying white, and how many of them come out black. That's the analogy. Right? And the answer is none of them. And strangely, if I take this thing, which seems to just attenuate, this is our middle box here, and I just stuff it in between them, I can get something to come out, even though I still have crossed polarizers on the side. So you can see the middle region is now brighter, and you can still see the dark corners there of the crossed polarizers. And as I turn this guy around, I can make that better or worse. The maximum is somewhere right there, and it goes off again. So this is a way of understanding our electron sorting hyper-intelligent monkeys in terms of polarizations. And here it's just a vector projected on another vector, projected on another vector, something everybody knows how to do. So here's the polarization analogy of this Jan-Garlock experiment.
All right. Awesome. So the polarization analogy for interference effects in quantum mechanics is a canonical one in the text of quantum mechanics. So you'll find lots of books talking about this. It's a very useful analogy, and I encourage you to read more about it. We won't talk about it a whole lot more, but it's a useful one. All right, before I get going, any questions from last lecture? Last lecture was pretty much self-contained. It was experimental results. No, nothing? All right. The one thing that I want to add to the last lecture, the one last experimental observation, is I glossed over something that's kind of important, which is the following. So we started off by saying, look, we know that if I have a ray of light, it's a wave, it's an electromagnetic wave, and it has some wavelength lambda. And yet the photoelectric effect tells us that in addition to having a wavelength lambda, the energy, it has a frequency as well, a frequency in time. And the photoelectric effect suggested that the energy is proportional to the frequency. And we wrote this as h nu. And h bar is equal to h upon 2 pi. And omega is equal to 2 pi nu. Okay, so this is just the angular frequency rather than the number per time frequency. And h bar is the reduced Planck constant. So I'll typically write h bar omega rather than h nu, because these 2 pi's will just cause us endless pain if we don't use the bar. Anyway, so to an electromagnetic wave, we have a wavelength and a frequency. And the photoelectric effect led us to predict that the energy is linearly proportional to the frequency with linear proportionality coefficient h bar, Planck's constant. And the momentum is equal to h upon lambda, h upon lambda, also known as, let's see, I'm going to write this as h bar k, which is equal to h upon lambda, where here again h bar is h upon 2 pi, and so k is equal to 2 pi upon lambda. So k is called the wave number, and you should have seen this in 803. So these are our basic relations for light. We know that light, as an electromagnetic wave, has a frequency and a wavelength, or a wave number, an inverse wavelength. And the claim of the photoelectric effect is that the energy and the momenta of that light are thus quantized, that light comes in chunks. So it has a wave-like aspect, and it also has properties that are more familiar from particles. Now, early on, shortly after Einstein proposed this, a young French physicist named de Broglie said, well, look, OK, this is true of light. Light has both wave-like and particle-like properties. Why is it just light? The world would be much more parsimonious if this relation were true not just of light, but also of all particles. I am thus conjecturing with no evidence whatsoever that, in fact, this relation holds not just for light, but for any object. Any object with momentum p has associated to a wavelength or a wave number, which is p upon h bar. Every object that has energy E has associated with it a wave with frequency omega. To those electrons that we send through the Davis-Germer experiment apparatus, which are sent in with definite energy, there must be a frequency associated with it, omega, and a wavelength, lambda, associated with it. And what we saw from the Davis-Germer experiment was experimental confirmation of that prediction, that electrons have both particulate and wave-like features simultaneously. So these relations are called the de Broglie relations, or de Broglie. I leave it up to you to decide how to pronounce that. And those relations are going to play an important role for us in the next few lectures. I just want to give them a name and a little context. This is a good example of parsimony and elegance, theoretical elegance, leading you to an idea that turns out to be true of the world. Now, that's a dangerous strategy for finding truth, right? Boy, wouldn't it be nice if, right? Wouldn't it be nice if, you know, we didn't have to pay taxes, but we also had Medicare? But of course, you know, so that's not a terribly useful guide all the time, but sometimes it really does lead you in the right direction. This is a great example of physical intuition, wildly divorced from experiment, pushing you in the right direction. I'm making it sound a little more shocking than, well, it was shocking. It was just shocking. OK, so with that said, let me introduce the moves for the next few lectures. For the next several lectures, here's what we're going to do. I am not going to give you experimental motivation. I've given you experimental motivation. I'm going to give you a set of rules, okay? A set of postulates. These are going to be the rules of quantum mechanics. And what quantum mechanics is for us is a set of rules to allow us to make predictions about the world, okay? And these rules will be awesome if their predictions are good. And if their predictions are bad, these rules will suck. Right? We will avoid bad rules to the degree possible. I'm going to give you what we've learned over the past 100 years, wow, of developing quantum mechanics. That is amazing. Wow, OK, yeah, over the past 100 years of developing quantum mechanics. And I'm going to give them to you as a series of postulates, and then we're going to work through the consequences. And then we're going to spend the rest of the semester studying examples to develop an understanding for what the rules of quantum mechanics are giving you. OK? So we're just going to scrap classical mechanics and start over from scratch. So let me do that. And to begin, let me start with the definition of a system. And to understand that definition, I want to start with classical mechanics as a guide. So in classical mechanics, let's think about the easiest classical system you can, just a single particle sitting somewhere. In classical mechanics of a single particle, how do you specify the configuration or the state, just different word for the same thing? How do you specify the configuration or state of the system?
Position and momentum.
A specified position and momentum, exactly. So in classical mechanics, if you want to completely specify the configuration of the system, all you have to do is give me x and p for my particle. And if you tell me this, I know everything. If you know these numbers, you know everything. In particular, what I mean by saying you know everything is that if there's anything else you want to measure, the energy, for example, the energy is just some function of the position and the momentum. And if you know the position and the momentum, you can unambiguously calculate the energy. Similarly, the angular momentum, which is a vector, you can calculate it if you know x and p, which is just, r cross p. Okay? So this gives you complete knowledge of the system. There's nothing more to know if you know that data. Now, there are certainly still questions that you can't answer given knowledge of x and p. Okay? For example, are there 14 invisible monkeys standing behind me? I'm here. I'm not moving. Are there 14 invisible monkeys standing behind me? You can't answer that. It's a stupid question, right? OK, let me give you another example. The electron is x and p, some position. Is it happy? right? So there are still questions you can't answer. The point is complete knowledge of the system to answer any physically observable question, any question that could be meaningfully turned into an experiment. The answer is contained in knowing the state of the system. Cool? OK? But this can't possibly be true in quantum mechanics because, as you saw in the problem set and as we've discussed previously, there's an uncertainty relation which says that your knowledge, or your uncertainty rather, in the position of a particle quantum mechanically, or I'm not even going to say quantum mechanically. I'm just going to say the real world. OK? So in the real world, our uncertainty in the position of our point-like object and our uncertainty in the momentum is always greater than or roughly equal to something that's proportional to Planck's constant. Okay? You can't be arbitrarily confident of the position and of the momentum simultaneously. You worked through a good example of this on the problem set. We saw this in the two-slit experiment and the interference of electrons. This is something we're going to have to deal with. So as a consequence, you can't possibly specify the position and the momentum with confidence of a system. You can't do it. Okay? This was a myth. It was a good approximation, turned out to be false. So the first thing we need is to specify the state, the configuration of a system. So what specifies the configuration of a system? And so this brings us to the first postulate. The configuration or state of a system. And here I'm, again, just for simplicity, I'm going to talk about a single object, of a quantum object. Is completely specified. Completely specified by a single function, a wave function, which I will denote generally psi of x, which is a complex function. Okay? The state of a quantum object is completely specified once you know the wave function of the system, which is a function of position. Let me emphasize that this is a first pass at the postulates. What we're going to do is go through the basic postulates of quantum mechanics, then we'll go through them again and give them a little more generality, and then we'll go through them again and give them full generality. That last pass is 805. Okay? So let me give you some examples. Let me just draw some characteristic wave functions. Okay? And these are going to turn out to be useful for us. Yeah, good. So for example, consider the following function. So here is 0, and we're plotting as a function of x, and I'm plotting the real part of psi of x. Okay? So first consider a very narrowly supported function. It's basically 0 everywhere, except it has some particular spot at what I'll call x1. Okay? Here's another wave function, 0. It's basically 0, except for some special spot at x2. Okay, and again, I'm plotting the real part of psi. And I'm plotting the real part of psi because A, psi is a complex function. At every point, it specifies a complex number. And B, I can't draw complex numbers. So to keep my head from exploding, I'm just plotting the real part of the wave function. But you should never forget that the wave function is complex. So for the moment, I'm going to assume that the imaginary part is 0. I'm just going to draw the real parts. So let me draw a couple more examples. What else could be a good wave function? Well, those are fine. What about, again, we want a function of x, and I'm going to draw the real part. Okay. And another one. So this is going to be a perfectly good wave function. Okay. And let me draw two more. So what else could be a reasonable wave function? Well, This is harder than you'd think. Oh, God. OK, so that could be the wave function. I don't know. And that is actually my signature. My wife calls it a little gift. OK, so here's the deal. Psi is a complex function. Psi also needs to not be a stupid function. OK, so you have to ask me, look, could it be any function, any arbitrary function? So this is going to be a job for us. We're going to have to define what it means to be a not stupid function. Well, this is a completely reasonable function. It's fine. This is a reasonable function. Another reasonable function, reasonable. That's a little weird, but it's it's not horrible. That's stupid, right? That is so we're going to give you we're going to have to come up with a good definition of what not stupid means. So fine, these are all functions. One of them is multi-valued, and that looks a little worrying, but they're all functions. So here's the problem. What does it mean? So postulate 2. The meaning of the wave function is that the probability that upon measurement the object is found at the position x is equal to the norm squared of psi of x. Okay? If you know the system is described by the wave function psi, and you want to look at point x, you want to know with what probability will I find the particle there, the answer is psi squared. Notice that this is a complex number, but absolute value squared, or norm squared of a complex number, is always a real non-negative number. And that's important, because we want our probabilities to be real non-negative numbers. It could be 0, right? It could be 0 chance of something. It can't be -7 chance. OK. Incidentally, there also can't be probability 2, right? So that means that the total probability had better be normalized. So let me just say this in words, though, first. So p, which is the norm squared of psi, determines the probability, and in particular the probability density, that the object in state psi, in the state given by the wave function psi of x, will be found. At x. OK? So there's the second postulate. So in particular, when I say it's a probability density, what I mean is the probability that it is found between the position x and x plus dx is equal to p of x dx, okay? Which is equal to psi of x squared dx, okay? Does that make sense? So the probability that it's found in this infinitesimal interval is equal to this density times dx, or psi squared dx. Now again, we need, it's crucial that the wave function is in fact properly normalized, because if I say, look, something could either be here or it could be here, what's the sum of the probability that it's here plus the probability that it's here? It had better be 1, right? Or there's some other possibility. So probabilities have to sum to 1. Total probability that you find something somewhere must be 1. So what that tells you is that the total probability, which is equal to the integral over all possible values of x. So if I sum over all possible values of x, p of x, all values, should be equal to 1. And we can write this as integral dx over all values of x. And I write all here rather than putting minus infinity to infinity, because some systems will be defined from 1 to -1. Some systems will be defined from minus infinity to infinity. All just means integrate over all possible values. Hold on one sec. Of psi squared. Yep?
Can you please use different notation for probability density and probability?
I'm not going to. Probability density is going to have just one argument, and total probability is going to have an interval as an argument. Okay, so they're distinct, and this is just the notation I like. Other questions? OK. Just as a side note, what are the dimensions of the wave function? So everyone think about this one for a second. All right, what are dimensions?
Is it 1 over the square root of length?
Awesome. Yes, it's 1 over root length. Dimensions of psi are 1 over root length. And the way to see that is that this should be equal to 1. It's a total probability. This is an infinitesimal length, so this has dimensions of length. This has no dimension, so this must have dimensions of 1 over length. And so psi itself of x must have dimensions of 1 over root length. Now, something I want to emphasize, I'm going to emphasize over and over in this class, is dimensional analysis. You need to become comfortable with dimensional analysis. It's absolutely essential. Okay? It's essential for 2 reasons. First off, it's essential because I'm going to be merciless in taking off points if you do write down a dimensionally false thing. If you write down something on a problem set or an exam that's like a length is equal to a velocity, ooh, not good. But the second thing is, forget the fact that I'm going to take off points. Dimensional analysis is an incredibly powerful tool for you. You can check something that you've just calculated, and even better yet, sometimes you can just avoid a calculation entirely by doing a dimensional analysis and seeing that there's only one possible way to build something of dimensions length in your system. So we'll do that over and over again. But this is a question I want you guys to start asking yourselves at every step along the way of a calculation. What are the dimensions of all the objects in my system? Something smells like smoke. OK, so with that said, if that's the meaning of the wave function, what physically can we take away? What physically can we take away from knowing these wave functions? Well, if this is the wave function, let's draw the probability distribution. What's the probability distribution? P of x. And the probability distribution here is really very simple. It's, again, 0 squared is still 0. So it's still just a big spike at x1. And this one is a big spike at x2. OK? Everyone cool with that? So what do you know when I tell you that this is the wave function describing your system? You know that with great confidence, you will find the particle to be sitting at x1 if you look. Right? So what this is telling you is you expect x is roughly x1, and our uncertainty in x is small. Everyone cool with that? Similarly here, you see that the position is likely to be x2, and your uncertainty in your measurement, or your confidence in your prediction is another way to say it, is quite good, so your uncertainty is small. Now what about these guys? Well, now it's the norm squared. I need to tell you what the wave function is. Here, the wave function that I want, and so here's 0. The wave function is e to the I k1x. And here, the wave function is equal to e to the I k2x. And remember, I'm drawing the real part because, of practical limitations. So the real part is just a sinusoid, or in fact, a cosine. And similarly, here, the real part is a cosine. And I really should put 0 in the appropriate place, but that worked out well. OK, good. So now the question is, what's the probability distribution, P of x, associated to these wave functions? So what's the norm squared of minus e to the I kx? If I have a complex number, phase, e to the I alpha, and I take its norm squared, what do I get? 1, right? So remember complex numbers. If we have a complex number alpha, if we have a complex number beta, then beta squared is by definition beta complex conjugate times beta. So e to the I alpha, if the complex conjugate is e to the minus I alpha, e to the I alpha times e to the minus I alpha, they cancel out, that's 1. OK? So if this is the wave function, what's the probability distribution? Well, it's 1. It's independent of x, right? So from this, we've learned 2 important things. The first is this is not properly normalized. That's not so key. But the most important thing is, if this is our wave function, and we subsequently measure the position of the particle, we look at it, we say, ah, there's the particle, where are we likely to find it? Yeah, it could be anywhere, right? So what's the value of x you expect? Typical x. I have no idea. No information whatsoever. None. But, and correspondingly, what is our uncertainty in the position of x that we will measure? It's very large, exactly. Now, in order to tell you it's actually infinite, I need to stretch this off and tell you that it's actually constant off to infinity, and my arms aren't that long, so I'll just say large. Similarly here, if our wave function is e to the I k2x, here k2 is larger, the wavelength is shorter. What's the probability distribution? It's, again, constant. Right? So this is 0, 0. So again, x, we have no idea. And our uncertainty in the x is large. And in fact, it's very large. Everyone cool with that? Questions? What about these guys? OK, this is the real challenge. OK, so if this is our wave function, and let's just say that it's real, hard as it is to believe that, then what's our probability distribution? Well, it's something like I don't know. It's something. You get the point. OK, so where is so if this is our probability distribution, where are we likely to find the particle? Well, now it's a little more difficult, right? Because we're unlikely to find it here. Well, it's reasonably likely to find it here. Unlikely here, reasonably likely, unlikely, like, you know, it's a mess. So where is this? I'm not really sure. What's our uncertainty? Well, our uncertainty is not infinite, right? Because, OK, my name ends at some point. So this is going to go to 0. It'll go to 0. So whatever else we know it's in this region. So it's, you know, it's not infinite. It's you know, not small, we'll say. But it's not arbitrarily small. It's not tiny. Or sorry, it's not gigantic. That's what I meant. It's not, our uncertainty is not gigantic. Not gigantic. But it's still pretty non-trivial because you know, I can say with some confidence that it's more likely to be here than here, but I really don't know which of those peaks it's going to be found. Right? OK, now what about this guy? What's the probability distribution? Well, now you see why this is a stupid wave function. Because it's multiply valued. It has multiple different values at every value of x. So what's the probability? Well, maybe it's √2, maybe it's 1 over √3. I'm really not sure. Right? So this tells us an important lesson. This is stupid. And what I mean by stupid is it is multiply valued. So the wave function, we've just learned a lesson, should be single valued. OK? And we will explore some more on your problem set, which will be posted immediately after lecture. There are problems that walk you through a variety of other potential pathologies of the wave function and guide you to some more intuition. For example, the wave function really needs to be continuous as well. You'll see why. All right. Questions at this point? No? OK. So these look like pretty useful wave function because they correspond to the particle being at some definite spot. And I, for example, at a reasonably definite spot. These 2 wave functions, though, look pretty much useless because they give us no information whatsoever about what the position is. Everyone agree with that? Except, remember the de Broglie relations. The de Broglie relations say that associated to a particle is also some wave. And the momentum of that particle is determined by the wavelength. It's inversely related to the wavelength. It's proportional to the wave number. And the energy is proportional to the frequency. Now, look at those wave functions. Those wave functions give us no position information whatsoever, but they have very definite wavelengths. Those are periodic functions with definite wavelengths. In particular, this guy has a wavelength of from here to here. Yeah? It has a wave number k, k1. So that tells us that if we measure the momentum of this particle, we can be pretty confident, because it has a reasonably well-defined wavelength corresponding to some wave number k, 2 pi upon the wavelength. It has some momentum, and if we measured it, we should be pretty confident that the momentum will be h bar k1. Ever agree with that? Looks like a sine wave. And de Broglie tells us that if you have a wave with wavelength lambda, that corresponds to a particle having momentum p. Now, how confident can we be in that estimation of the momentum? Well, if I tell you it's e to the ikx, that's exactly a periodic function with wavelength lambda, 2 pi upon k. So how confident are we? Pretty confident. So our uncertainty in the position, or in the momentum, is tiny. Everyone agree? Similarly, for this wave, again, we have a wavelength. It's a periodic function, but the wavelength is much shorter. If the wavelength is much shorter, then k is much larger. The momentum is much larger. So the momentum we expect to measure, which is roughly h bar k, 2, is going to be much larger. What about our uncertainty? Again, it's a perfect periodic function, so our uncertainty in the momentum is small. Everyone cool with that? And that comes, again, from the de Broglie relations. So, good. So questions at this point? You guys are real quiet today. All right. No questions? Yeah?
So delta p is 0, basically?
It's pretty small. Now, again, I can't, I haven't drawn this off to infinity, but if it's exactly e to the ikx, then yeah, it turns out to be 0. Now, an important thing, so let me rephrase your question slightly. So the question was, is delta p 0? Is it really 0? So here's the problem for us right now. We don't have a definition of delta p. Right? So what is the definition of delta p? I haven't given you one. So here, when I've said delta p is small, what I mean is, intuitively, just by eyeball, our confidence in that momentum is pretty good, using the de Broglie relations. I have not given you a definition, and that will be part of my job over the next couple of lectures. Very good question. Yeah?
So how would you encode noise in that function? Would
Awesome.
you just have different wavelengths
Yeah.
as you go along?
Awesome. So for example, this, does it have a definite wavelength? Not so much. So hold that question and wait until you see the next examples that I put on this board. And if that doesn't answer your question, ask it again, because it's a very important question. OK.
When you talk about like a photon with
Yes.
like a given, well, you always say like a photon has a certain frequency. Doesn't that mean that it must be a wave because you have to like fix the wave number k?
Awesome question. Does every wave packet of light that hits your eye, does it always have a single unique frequency? No, you can take multiple frequency sources and superpose them. An interesting choice of words I used there. Right, so the question is, since light has some wavelength, does every chunk of light have a definite? This is the question roughly. Yeah. So and the answer is light doesn't always have a single. You can have light coming at you that has many different wavelengths and put it in a prism and break it up into its various components. Right. So you can have a superposition of different frequencies of light. We'll see the same effect happening for us. OK. So again, de Broglie made these. There we go. De Broglie made this conjecture that E is h bar omega and P is h bar k. This was verified in the Davison-Germer experiment that we ran. But here, one of the things that's sort of latent in this is what he means is, look, associated to every particle with energy E and momentum P is a plane wave of the form e to the I kx minus omega t. Okay, and this is properly in 3 dimensions, should be k dot x. But at this point, this is an important simplification. For the rest of 804, we are going to be doing one-dimensional, or for the rest of 804 until otherwise specified, we are going to be doing one-dimensional quantum mechanics. So I'm going to remove arrow marks and dot products. There's going to be one spatial dimension and one time dimension. we're always going to have just one time dimension, but sometimes we'll have more spatial dimensions. But it's going to be a while till we get there. So for now, we're just going to have kx. So this is a general plane wave. And what de Broglie really was saying is that somehow associated to the particle with energy E and momentum p should be some wave, a plane wave, with wave number k and frequency omega, and that's the wave function associated to it. Okay. The thing is, not every wave function is a plane wave. Some wave functions are well localized. Some of them are just complicated morasses. Okay. Some of them are just a mess. Okay. So now is the most important postulate in quantum mechanics. I remember vividly when when I took the analog of this class, it was called Physics 143A at Harvard, and the professor at this point said, I know him well now, he's a friend, he said, "This is what quantum mechanics is all about." And I was so psyched, and then he told me, and it was like, that's ridiculous. Seriously? That's what quantum mechanics is all about? So I always thought, like, this is some weird thing where, like, old physicists go crazy. But it turns out, I'm going to say exactly the same thing. This is the most important thing in all of quantum mechanics. It is all contained in the following proposition. Everything. The two-slit experiments, the box experiments, all the cool stuff in quantum mechanics, all the strange and counterintuitive stuff comes directly from the next postulate. So here it is. I love this. 3. Put a star on it. Given 2 possible wave functions or states, I'll say configurations of a quantum system, I wish there was like Ride of the Valkyries, playing in the background. So, of a quantum system corresponding to 2 distinct wave functions Okay, f with an upper ns is going to be my notation for functions, because I have to write it a lot. Psi1 and psi2. And I'll say of x. The system is down. The system can also be in a superposition of psi1 and psi2. Where alpha and beta are complex numbers. Given any 2 possible configurations of the system, there is also an allowed configuration of the system corresponding to being in an arbitrary superposition of them. If an electron can be hard and it can be soft, it can also be in an arbitrary superposition of being hard and soft. And what I mean by that is that hard corresponds to some particular wave function. Soft will correspond to some particular wave function. And a superposition corresponds to a different wave function, which is a linear combination of them. Yeah?
Does the linear combination also have to be normalized?
Yeah, OK, that's a very good question. So A and B, alpha and beta are some complex numbers subject to the normalization condition. So indeed, this wave function should be properly normalized at the end. Now, let me step back for a second. There's an alternate way to phrase the probability distribution here, which goes like this, and I'm going to put it here. The alternate statement of the probability distribution is that the probability density at x is equal to psi of x norm squared divided by the integral over all x dx of psi squared. Okay? So notice that if we've properly normalized the wave function, this denominator is equal to 1. But if we haven't properly normalized, and so it's not there, right? And then it's equivalent. But if we haven't properly normalized it, then this probability distribution is automatically properly normalized, because this is a constant. When we integrate the top, that's equal to the bottom. It integrates to 1. Cool? So I prefer, personally, in thinking about this for the first pass, to just require that we always be careful to choose some normalization. That won't always be easy. And so sometimes it's useful to forget about normalizing and just define the probability distribution in that way. Is that cool? OK. This is the beating soul of quantum mechanics. Everything in quantum mechanics is in here. Everything in quantum mechanics is forced on us from these few principles and a couple of requirements of matching to reality. Yeah?
When you do this sum like linear sum of two wave functions,
yes.
Can you get like interference?
Yes. Excellent. So the question is, when you have a sum of two wave functions, can you get some sort of interference effect? And the answer is absolutely. And that's exactly what we're going to do next. So in particular, let me look at a particular pair of superpositions. So let's swap these boards around. The parallelism is a little more obvious. OK. So let's scrap these rather silly wave functions and come up with something that's a little more interesting. So instead of using those as characteristic wave functions, I want to build superpositions. So in particular, I want to start by taking an arbitrary, both these wave functions is a simple interpretation. This corresponds to a particle being here. This corresponds to a particle being here. I want to take a superposition of them. So here's my superposition. OK. Oops. Let's try that again. Good. And my superposition, so here's 0, and here's x1, and here's x2. My superposition is going to be some amount times the first one plus some amount times the second one. There's a superposition. Similarly, I could have taken a superposition of the two functions on the second chalkboard. And again, I'm taking a superposition of the complex e to the ik1x and e to the ik2x, and then taking the real part. Okay. So that's a particular superposition, particular linear combination. So now let's go back to this. This was a particle that was here. This was a particle that was there. When we take the superposition, what is the probability distribution? Where is this particle? Well, there's some amplitude that it's here, and there's some amplitude that it's here. And there's rather more amplitude that it's over here, but there's still some probability that it's over here, right? Where am I going to find the particle? I'm not so sure anymore. It's either going to be here or here, but I'm not positive. And it's more likely to be here than it is to be here, but not a whole lot more. So where am I going to find the particle? Well, now we have to define this, where I'm going to find the particle. Look, if I did this experiment a whole bunch of times, it'd be over here more than it would be over here. So the average will be somewhere around here. It'll be in between the two. So x is somewhere in between. That's where we expect to find it. On average. Okay. What's our uncertainty in the position? Well, it's not that small anymore. It's now, of order x1 minus x2. Everyone agree with that? Bless you. Now, what about this guy? Well, does this thing have a period? Does it have a single wavelength, sorry? No. This is like light that comes at you from the sun. It has many wavelengths. In this case, it has just two. I've added those two together. So this is a plane wave, which is psi is e to the ik1x plus e to the ik2x. Okay. So in fact, it has two wavelengths associated with it, lambda 1 and lambda 2. And so the probability distribution now, if we take the norm squared of this, the probability distribution now which is the norm squared of this guy, is no longer constant, but there's an interference term. And let's just see how that works out. Let me be very explicit about this. Note that the probability in our superposition of psi1 plus psi2, which I'll call e to the I k1x plus e to the I k2x, the probability is equal to the norm squared of the wave function, which is the superposition psi1 plus beta psi2, which is equal to alpha squared psi1 squared plus beta squared psi2 squared plus alpha star, whoops, psi1 star, actually let me write this over here, plus alpha star psi1 star beta psi2 plus alpha psi1 beta star psi2 star, where star means complex conjugation. But notice that this is equal to, that first term is alpha squared times the first probability, or the probability of this thing, of alpha psi1. So this is equal to probability 1. This term, beta squared psi2 squared, is the probability that the second thing happens. But these terms can't be understood in terms of the probabilities of psi1 or the probability of psi2 alone. They're interference terms. Okay? So the superposition principle, together with the interpretation of the probability as the norm squared of the wave function, gives us a correction to the classical addition of probabilities, which is these interference terms. Everyone happy with that? Now here's something very important to keep in mind. These things are norm squareds of complex numbers. That means they're real, but in particular they're non-negative. So these two are both real and non-negative. But what about this? This is not the norm squared of anything. However, this is its complex conjugate. When you take something in its complex conjugate, you add them together, you get something that's necessarily real. But it's not necessarily positive. So this is a funny thing. The probability that something happens if we add together two configurations, if we superpose two configurations, has positive probability terms, but it's also got terms that don't have a definite sign, that could be negative. It's always real. And you can check that this quantity is always greater than or equal to 0. It's never negative, the total quantity. So remember Bell's inequality that we talked about? Bell's inequality said, look, the probability of one thing happening, if we have the probability of one thing happening being P1 and the probability of the other thing happening being P2, the probability of both things happening is just P1 plus P2. And here we see that in quantum mechanics, probabilities don't add that way. The wave functions add, and the probability is the norm squared of the wave function. The wave functions add, not the probabilities. And that is what underlies all of the interference effects we've seen. And it's going to be the heart of the rest of quantum mechanics. So you're probably all going in your head, more or less like I was when I took intro quantum, like, yeah, but I mean, it's just, you're adding complex numbers. But trust me on this one. This is where it's all starting. OK, so let's go back to this. Similarly, let's look at this example. We've taken the norm squared, and now we have an interference effect. And now our probability distribution, instead of being totally trivial and containing no information, our probability distribution now contains some information about the position of the object. It's likely to be here. It is unlikely to be here, likely and unlikely. We now have some position information. We don't have enough to say where it is, but x is, we have some information. OK. Now, our uncertainty is still gigantic. Delta x is still huge. But OK, we just added together two plane waves. Yeah?
Why is the probability not up, big, small, small, big, small?
Excellent. This was the real part of the wave function, right? And the wave function is a complex quantity. When you take e to the I k1, let me do this on the chalkboard. When we take e to the I k1x plus e to the I k2x, let me write this slightly differently. E to the I a plus e to the I b, and take its norm squared. OK? So this is equal to, I'm going to write this in a slightly more suggestive way, the norm squared of e to the I a times 1 plus e to the I b minus a. OK, norm squared. Oops, parentheses, norm squared. So first off, the norm squared of a product of things is the product of the norm squareds. So I can do that. And this overall phase, the norm squared of a phase is just 1. So that's just 1. So now we have the norm squared of 1 plus a complex number. OK? And so this is the norm squared of 1 is going to give me 1. The norm squared of the complex number is going to give me 1. And the cross terms are going to give me the real part, twice the real part, of e to the I b minus a, which is going to be equal to cosine of b minus a. OK? And so what you see here is that you have a single frequency in the superposition. Cool? OK. So again, here, oh, so good. So our uncertainty is large. So let's look at this second example in a little more detail. By superposing two states with wavelength lambda1 and lambda2, or k1 and k2, wow, with wavelengths lambda1 and lambda2, we get something that's, OK, it's still not well localized. We don't know where the particle is going to be, but it's better localized than it was before, right? What happens if we superpose with 3 wavelengths, or 4, or more? So for that, I want to pull out a Mathematica package. And you guys should all have seen Fourier analysis in you should all have seen Fourier analysis in 1803, but just in case, I'm putting on the web page, on the Stellar page, a notebook that walks you through the basics of Fourier analysis in Mathematica. You should all be fluent in Mathematica. If you're not, you should probably, oops, come up to speed on it. That's not what we wanted. Let's try that again. There we go. Oh, that's awesome. Or by awesome, I mean not. It's coming. OK, good. OK, I'm not even going to mess with the screens after last time. So I'm not going to go through the details of this package, but what this does is walk you through the superposition of wave packets. So here, I'm looking at the probability distribution coming from summing up a bunch of plane waves with some definite frequency. So here it's just 1. OK? That's one wave. So first we have, let me make this bigger. Yes, stupid Mathematica tricks. So here we have the wave function, and here we have the probability distribution, the norm squared. OK? And it's sort of badly normalized here. So that's for a single wave, and as you see, the probability distribution is constant. And that's not 0, that's 0.15. It's just I arbitrarily normalized this. So let's add 2 plane waves. And now what you see is the same effect as we had here. You see a slightly more localized wave function. And now you have a little bit of structure in the probability distribution. So there's the structure in the probability distribution. We have a little more information about where the particle is. More likely to be here than it is to be here. Let's add one more. And as we keep adding more and more plane waves to our superposition, the wave function and the probability distribution associated with it become more and more well localized. Yeah? Until as we go to very high numbers of plane waves that we're superposing, we get an extremely narrow probability distribution, and wave function for that matter, extremely narrow, corresponding to a particle that's very likely to be here and unlikely to be anywhere else. Everyone cool with that? What's the expense? What have we lost in the process? Well, we know with great confidence now that the particle will be found here upon observation. But what will its momentum be? Yeah, now it's a superposition of a whole bunch of different momenta. So if it's a superposition of a whole bunch of different momenta, that here, this is like superposition of a whole bunch of different positions, right? Likely to be here, likely to be here, likely to be here, likely to be here. What's our knowledge of its position? It's not very good. Similarly, now that we have superposed many different momenta with comparable strength, in fact, here they were all with unit strength, we now have no information about what the momentum is anymore. It could be anything in that superposition. So now we're seeing quite sharply the uncertainty relation. And here it is. Go back to the. So the uncertainty relation is now pretty clear from these guys. Whoops, that didn't work. Good. So the uncertainty relation is, and I'm going to leave it alone. This is enough for the Fourier analysis. But that Fourier package is available with extensive commentary on the Stellar webpage. Yeah?
Now, is that sharp definition in the position caused by the interference between all those waves and all that?
That's exactly what it is. Precisely. It's precisely the interference between the different momentum modes that leads to certainty in the position. That's exactly right. Yeah?
So as certain another position, we will not certain another momentum.
Exactly. Here we are. So in this example, we have no idea what the position is, but we're quite confident of the momentum. Here, we have no idea what the position is, but we have great confidence in the momentum. Similarly, here, we have less perfect confidence of the position, and here we have less perfect confidence in the momentum. It would be nice to be able to estimate what our uncertainty is in the momentum here and what our uncertainty is in the position here. So we're going to have to do that. That's going to be one of our next tasks. Okay. Other questions? Yeah?
This half of the part,
yes.
Blackboard, you said, obviously if we do it a bunch of times, we'll have more in the x2 than in the x1.
Yes.
The average, it will never physically be at that point.
Yeah, that's right. So because it's a probability distribution, it won't be exactly at that point, but it'll be nearby. Okay, so in order to be more precise, and so for example, for this, here's a quick question. How well do you know the position of this particle? Pretty well, right? But how well do you know its momentum? Well, so we'd all like to say not very, but tell me why. Why is your uncertainty in the momentum of the particle large? Yeah, but that's a cheat because we haven't actually proved Heisenberg's uncertainty principle. It's just something we're inheriting. I believe it too, but I want a better argument because I believe all sorts of crazy stuff. So I really do. So black holes, fluids, I mean, look, don't get me started. Yeah.
You can take the Fourier transform.
Yeah, excellent. OK, we'll get to that in just one sec. So before taking a Fourier transform, which is an excellent, so the answer was, just take a Fourier transform. It's going to give you some information. We're going to do that in just a moment. But before we do Fourier transform, just intuitively, why would de Broglie look at this and say, no, that doesn't have a definite momentum? Yeah, there's no wavelength, right? It's not periodic by any stretch of the imagination. It doesn't look like a thing with a definite wavelength. And de Broglie said, look, if you have a definite wavelength, then you have a definite momentum. And if you have a definite momentum, you have a definite wavelength. This is not a wave with a definite wavelength. So it is not corresponding to the wave function for a particle with a definite momentum. So our momentum is unknown. So this is large. And similarly here, our uncertainty in the momentum is large. Okay? So to do better than this, we need to introduce the Fourier transform. And I want to do that now. So you've all seen you should all have seen Fourier series in 803. Now we're going to do the Fourier transform. And I'm going to introduce this to you in 804 conventions in the following way. And the theorem says the following. We're not going to prove it by any stretch of the imagination. But the theorem says any function f of x that is sufficiently well behaved, it shouldn't be discontinuous, it shouldn't be singular, any reasonably well behaved non-stupid function f of x can be built by enough plane waves of the form e to the ikx. Enough may be infinite. So f of x, any function f of x can be expressed as 1 over root 2 pi. And this root 2 pi is a choice of normalization. Everyone has their own conventions, and these are the ones we'll be using in 804 throughout. Minus infinity to infinity dk f tilde of k e to the ikx. So here what we're doing is we're summing over plane waves of the form e to the ikx. These are modes with a definite wavelength, 2 pi upon k. f tilde of k is telling us the amplitude of the wave with wavelength lambda or wave number k. And we sum over all possible values. And the claim is any function can be expressed as a superposition of plane waves in this form. Cool? And this is for functions which are non-periodic on the real line rather than periodic functions on the interval, which is what you should have seen in 803. Now, conveniently, if you know f tilde of k, you can compute f of x by doing a sum. But suppose you know f of x and you want to determine what the coefficients are, the expansion coefficients. That's the inverse Fourier transform. And the statement for that is that f tilde of k is equal to 1 over root 2 pi integral from minus infinity to infinity dx f of x e to the minus I kx. Okay, and that's sometimes referred to as the inverse Fourier transform. Okay, and here's something absolutely essential. F tilde of k, the Fourier transform coefficients of f of x, are completely equivalent. If you know f of x, you can determine f tilde of k. And if you know f tilde of k, you can determine f of x by just doing a sum, by just adding them up. Okay? So now here's the physical version of this. Oh, I can't slide that up. The physical version of this, I'm now going to put here. Oh, no, I'm not. I'm going to put that down here. So the physical version of this is that any wave function good. Any wave function psi of x can be expressed as the superposition in the form psi of x is equal to 1 over root 2 pi integral from minus infinity to infinity dk psi tilde of k e to the ikx. Whoops. Of states or wave functions with a definite momentum. P is equal to h bar k. Okay. And so now it's useful to sketch the Fourier transforms of each of these functions. So in fact, we want this up here. So there is erasers. Carnage down there. So here we have the function and its probability distribution. Now I want to draw the Fourier transforms of these guys. So here's psi tilde of k, function of a different variable than of x, but nonetheless it's illuminating to draw them next to each other. And again, I'm drawing the real part. And here, x2, had I had my druthers about me, I would have put x2 at a larger value. Good. So it's further off to the right there. Huh. And similarly, I'm so loath to erase the superposition principle. But Fortunately, I'm not there yet. Let's look at the Fourier transform of these guys. So the Fourier transform of this guy is now, whoops, this is k psi tilde of k. Well, that's something with a definite value of k. And its Fourier transform, this is 0. There's k1. And for this guy, there's 0, k2. And now if we look at the Fourier transforms of these guys, see this way I don't have to erase the superposition principle. The Fourier transforms of these guys and the Fourier transform of this guy okay? So note that there's a sort of pleasing symmetry here. If your wave function is well localized, corresponding to a reasonably well-defined position, then your Fourier transform is not well localized, corresponding to not having a definite momentum. On the other hand, if you have definite momentum, your position is not well defined, but the Fourier transform has a single peak. The Fourier transform has a single peak at the value of k corresponding to the momentum of your wave function. Everyone cool with that? So here's a question. Sorry, there was a raised hand. Yeah.
Are we going to learn in this class how to determine the Fourier transforms of these non-stupid functions?
Yes, that will be your homework. On your homework is an extensive list of functions for you to compute Fourier transforms of, and that will be the job of problem sets and recitation. So Fourier series and computing, yeah, you know what's coming. So Fourier series are assumed to have been covered for everyone in 803 and 1803 in some linear combination thereof. And Fourier transforms, I couldn't help it. So Fourier transforms are slight embiggening of the space of Fourier series because we're not looking at periodic functions. Yeah.
So when we're doing like a Fourier transform of a wave function, we're basically writing it as a continuous set of like different waves. Can we write it as a discrete set, so like use a Fourier series?
Absolutely. So, however, what is true of a Fourier series? When you use a discrete set of momenta, which are linear, it must be periodic function, exactly. So the question is, do you always have to? So here, what we've done is we've said, look, we're writing our wave function, our arbitrary wave function, as a continuous superposition of a continuous value of possible momenta. This is absolutely correct. This is exactly what we're doing. However, that's kind of annoying because continuous, maybe you just want like one momentum and two momenta and three momenta. What if you want a discrete series? So discrete is fine, but if you make that discrete series integer related to each other, which is what you do with Fourier series, you force the function f of x to be periodic. And we don't want that in general because life isn't periodic. Thank goodness, right? I mean, there's like one film in which it, but so it's a good movie. So that's the essential difference between Fourier series and Fourier transforms. Fourier transforms are continuous in K and do not assume periodicity of the function. Okay. Other questions? Yeah?
So basically the Fourier transform associates amplitude and a phase for each of the individual momenta.
Precisely. Precisely correct. So let me say that again. So the question was, so a Fourier transform effectively associates a magnitude and a phase for each possible wave vector. And that's exactly right. So here, there's some amplitude and phase. This is a complex number because this is a complex function. There's some complex number, which is an amplitude and a phase, associated to every possible momentum going into the superposition. That amplitude may be 0. There may be no contribution for a large number of momenta, or maybe insignificantly small. But it is indeed doing precisely that. It's associated an amplitude and a phase for every plane wave with every different value of momentum. And you can compute before panicking. You can compute precisely what that amplitude and phase is by using the inverse Fourier transform. Right? So there's no magic here. You calculate it. You can use your calculator, literally. Hate that word. OK, so now here's a natural question. So if this is the Fourier transform of our wave function, this wave function, we already knew that this wave function corresponded to having a definite, from de Broglie, we know that it has a definite momentum, right? We also see that its Fourier transform looks like this. So that leads to a reasonable guess. What do you think the probability distribution, P of k, is, probability density, the probability density to find the momentum to have wave vector k, h bar k? Yeah, that's a pretty reasonable guess. So here's just, we're totally pulling this out of the dark, psi of k norm squared. OK, well, let's see if that works. So psi of k norm squared for this is going to give us a nice, well-localized function. And similarly, psi of k for this, and so that makes a lot of sense. It's exactly what we expected, right? Definite value of p with very small uncertainty. Similarly, here, definite value of p with very small uncertainty. Rock on. However, let's look at this guy. What is the expected value of p if this is the Fourier transform? Well, remember, we have to take the norm squared, and psi of k was e to the I kx1, the Fourier transform. You will do much practice on taking Fourier transforms on the problem set. Where did my eraser go? There it is. Farewell, principle 1. So what does norm squared of psi tilde look like? Well, just like before, the norm squared is constant, because the norm squared of a phase is constant. And again, the norm squared, so this is psi tilde of k norm squared. We believe, we're conjecturing, this is p of k. You will prove this relation on your problem set. You'll prove that it follows from what we've said before. And similarly, this is constant, e to the I kx2. OK? So now we have no knowledge of the momenta. So that also fits. The momenta is we have no idea, and uncertainty is large. And the momentum is we have no idea, and the uncertainty is large. So in all of these cases, we see that we satisfy quite nicely the uncertainty relation, small position momentum, large momentum uncertainty. Large position uncertainty, we're allowed to have small momentum uncertainty. And here, it's a little more complicated. We have a little bit of knowledge of the position, and we have a little bit of knowledge of the momenta. We have a little bit of knowledge of position, and we have a little bit of knowledge of the momenta. So we'll walk through examples with superposition like this on the problem set. OK. Last questions before we get going. OK, so I have two things to do before we're done. The first is, after lecture ends, I have clickers. And anyone who wants to borrow clickers, you're welcome to come down and pick them up in a first come, first served basis. I will start using the clickers in the next lecture. So if you don't already have one, get one now. But the second thing is, don't get started yet. I have a demo to do. And last time I told you, this is awesome. It's like I'm an experimentalist for a day. Last time I told you that one of the experimental facts of lice is one of the experimental facts of lice. One of the experimental facts of life is that there is uncertainty in the world, and that there is probability, that there are unlikely events that happen with some probability, some finite probability. And a good example of the randomness of the real world involves radiation. So hopefully you can hear this. Apparently, I'm not very radioactive. You'd be surprised at the things that are radioactive. Nope, got a little tick. Shh. OK. This is a plate sold at an Amish county fair. It's called Vaselineware, and it's made of local clays. it's got uranium in it. Okay? But even more exciting, and I just, I want to emphasize, exactly when something goes click. It sounds pretty random, and it's actually a better random number generator than anything you'll find in, Mathematica or C. In fact, for some purposes, the decay of radioactive isotopes is used as the perfect random number generator, because it really is totally random as far as anyone can tell. But here's my favorite. People used to eat off these. See you next time.